So it turns out that the problem of interpreting quantum mechanics before or after measurement and vis-a-vis observables, whether they are commuting, non-commuting, so whether they are simultaneous measurements. So this all, one is the, you just go in our way how we can interpret things and the sort of conundrums associated with it, which lead to causal anomalies, which can be done partially or in complete sense by those restrictive interpretations, as well as by taking the interpretations, the other interpretations. So it is also how we, an important problem in the how we construct knowledge in general. Maybe we are concentrating on the quantum mechanical knowledge, how we see quantum mechanics as an epistemic, as a truth, a fundamental truth of nature, as a fundamental theory of nature, and correspondingly as a knowledge of nature. But how we fundamentally construct knowledge, or how we abstract knowledge or extract knowledge from the world or about the world, is a sort of symbolism, and that symbolism is somehow encoded in a language. So there is a language, common language, or there is a quantum mechanical language, in which that language of the physical world, we express those expressions like observable, measurement, simultaneous. So these all are condensed in some language. So once we say language, so in language that, or linguistics, what we say, the symbolic, what statement or a measurement or an observation symbolizes, it has some symbol, in corresponding symbol. Symbolism is attached to it. So if it's just expressed in terse and logical manner, so it has its rules, which you can impose, or from which you can derive things, or from which things are implied. So same can be extended to quantum mechanical logic, quantum mechanical rules, which are imposed from nature, or our understanding of nature, and the measurements, how we can see them. So it's always a scene what's out there, and what we want to symbolically, the mapping of symbols to the exact what exists. So there is always some semantic residue. So it's not left. So it's so apart from, so in the linguistic analysis, or in the linguistic analysis of logicizing language, so there is the, once we try to make statements crisp and logical, something is left as a sort of residue. Or once we try to make it more, it will not become precise. The language will not become precise, or it will not become logical. So we have to just adjust with those compromises. So in that context, we can say quantum mechanics also introduces some compromises, and the logic of quantum mechanics, which is abstracted vis-a-vis those observables or measurements. So how we can express how these things, so we can partially do with some restrictive interpretations, which will just do away with causal anomalies, but it will leave something else the way. But if we want to encompass it whole, but it will not become tight and logical. So these conundrums can be expressed in today's class is observable language and quantum mechanical language. So maybe this observable language may be a very language, maybe a long, it's a very broad thing, but we'll concentrate on observable because it will just touch on the subjects of linguistics. And so, but we'll just touch on what do we mean by observable in the context of quantum mechanics. Yes, and certain precise measurements. For example, if the use of this thing. So, for example, observable language, the quantum can contain sentences like Geiger counter, Wilson chamber, photographic film, etc. Photographic film, measurement of dial, etc. Measurement of U. So measurement of U is there are some elementary expressions which are there. So that observation didn't, so measurement of U means measurement of psi as a wave function. That's it. So once we talk of measurements, what I should say, for example, once we talk of position Q of an electron, or momentum of an electron, momentum P of an electron. So, so you can say the truths and the falsehoods of the observable language are just we can import them into the truths and falsehoods of the observable language or quantum mechanical language. So quantum mechanical language, if there is truth and falsehood, we sometimes import those statements here. For instance, an electron has a position Q, has position Q. When we know the statement that electron has a position Q, it's a general statement. But we know that electron has a position Q after some measurement has been made. That's more precise statement. Measurement has been made which assigns this electron a position Q, so whether the measurement, the position was there, or we assigned our measurement what I should say, our measurement induced that value. So we normally say these are two things, but you can see that there is something is there which is not entirely just encompassing. So in the same way, we can have what is not only the truth content of those statements, but what are the meanings which we can derive or which are implied from them. So meanings of the observed language and meanings of the quantum mechanical language. So you have to be a bit nuanced in trying to decipher whether the meanings overlap or they slightly differ or disagree in that sense. So that in that context, in yesterday's class, we talked of something. When we talked of probabilities, we talked of probabilities as statistical statements. So even in probabilities, when we talked of relative probabilities, we said that we could not verify those chain causal statements vis-a-vis those probabilities, independent of whether quantum mechanical statements can be extended or not. So there was a probabilistic logic to it that those statements cannot, the assigned statements cannot be causally accurate in that sense. So you can say quantum mechanics and classical statistics where these probability conditions are involved. You can say we can say quantum mechanics can equal classical statements. Quantum mechanical statements can be equivalent, at least linguistically, for classical statements. When we say a physical situation S, now the simultaneous Q and P cannot be ascertained. This is the statement of quantum mechanical language. So the other part is that we can write predictive methods of quantum mechanics in this context are statistically complete in observational terms. For example, within observation language, you cannot raise a question with respect to what happens if an observation if an observation MQ on the position and MP on the momentum can happen simultaneously. For example, it will lead. For example, you cannot say a given temperature of a body was 5 degree as well as 1000 degrees simultaneously at a given time, at a given moment. So the common language may have a different thing. The quantum mechanical thing that we can think of simultaneous measurement for two given conjugate observables. Whether it's possible or not, in case of non-commutative, at least you can think of. But in classical terms, we cannot. It doesn't make sense. So we can say for predictive methods of quantum mechanics are statistically complete in observational terms. So whatever interpretations we are going to, we have to just see our measurements of quantum mechanics in the complete sense, not in the general contours of the normal language. For example, the statistical distribution of P of Q, for example, so even if a measurement may not be statistically complete in the quantum mechanical sense, in complete with respect to space-time description. So the idea of being statistically complete in the, for example, so although in the space-time and a statement may not be observationally, it may be statistically incomplete in the space-time descriptions, the way we have defined. So we cannot have the exact causality, cannot be inferred from that. But in terms of observational description, observational description vis-a-vis in terms of can we test it. So it can be still complete vis-a-vis how we can test those statements at least. Even though observationally you can, or statistically, it may be incomplete in that sense. So in that sense, there is a particular way how quantum mechanics somehow tries to do away with these inaccurate statements. We sometimes use the word meaningless. We sometimes even use the word indeterminate. So when you say indeterminate, it's not that something cannot be determined, or it's something a sort of nothing as a ex nihilo statement, but it means you restrict your observations or statements along particular direction. So you don't, in your fundamental assumptions, take that statement in the wider sense. You allow the validity of statement to exist in that narrow regime and exclude other things from the beginning, even though that's a weaker statement. So it has not to be understood in the language sense, commonsensical language, that it's indeterminate or there is in that sense. And we can have a particular, this entire discussion, one important point which is very much to be seen is Bohr-Heisenberg statement, you can say, or which this book has tried to see it that way. Bohr-Heisenberg statement says which is also a definition 4, it says that the result of measurement represents the value of measured entity immediately after measurement. So the result of measurement represents the value of measured entity immediately after the measurement. It is not prior to measurement, whatever the value might have been. So the question is whether that value is the same value but what we have measured. So that's another part of the thing. So we are not interested in that. So what we are saying is that we will only take the value which is after measurement. So it's after measurement. So once we do this considerations, so a lot of things, for example, even we don't even account for whether our measurement somehow disturbed the actual value which was there of that thing. And what we are measuring is not the actual way; it's the way, it's the measured thing plus that disturbance, or the disturbed measurement which we have measured. So we are not even interested in that. So we'll just concentrate on that. We'll take that. And we don't even say, for example, that observed is simultaneously also in conjugate sense related to that unobserved. So if you have a parameter, you have a conjugate parameter. They are related. So we are not saying that whether this measurement which we have had a value, is it somehow has to do something with its that undisturbed thing, unobserved thing, which in an interpolated sense is related with that parameter, or P with Q, E with T, so on and so forth. So we leave these things as we cannot say they are deliberately unanswerable, but we say they are deliberately they are left unanswered in this Bohr-Heisenberg interpretation, or whatever you might call it. So in that sense, we say that so you can say we can say Q represents a value existing between two measurements, whereas P represents a value existing after second measurement, when the value is of Q is no longer a value. So it's that question is that it's what I have said. It's not before measurement. It's not measurement after. It's what we measure things. For example, if we measure P first, Q first, then P. Then the obtained values of Q and P are not, they cannot be considered simultaneous, and that's fine. Only Q represents the value which was existing before measurements. So we leave it. So what? So that's it. So it's a bit contrived. So we'll just leave this thing. But one statement we can say in Bohr-Einstein statement is, if Q has been measured, so we do not know the value of P. So this lack of knowledge is considered in Bohr-Heisenberg relation as interpretation as statement of P is meaningless. We don't account that in that quantum mechanical language. Not meaningless in the commonsensical terms, but meaningless in the quantum mechanical terms. Now, in a physical state, if a state is not preceded by a measurement of an entity, any statement about that entities. So if I write this is definition 4, definition 5 says that if in a physical state, so you have to be conscious. It's not meaningless in that in the language sense. It's meaningless in the quantum mechanical sense. Yes. We don't take account of it from ab initio. So in a physical state, not preceded by a measurement, of an entity, any statement about a value of entity U is meaningless. In a physical state not preceded by a measurement of a entity U, any statement about the value of entity U is meaningless. So what was existing prior to the measurement, we don't fundamentally account to it. So it's also called Bohr-Heisenberg interpretation by a restricted meaning. We restrict things. We don't take all paths. We take the path which is assigned by that measurement after this thing. So we don't take a statement in the general sense, we take statement in the particular sense. So this all leads to some another language. The way we construct truth tables, or Boolean algebra or Boolean logic truth. So we can have a statement what is to be taken, and if there are two statements, they are colliding, what is the net statement which will come out of it. So if we have an observed language, and we have a measurement, and what will be the quantum mechanical language. In that sense, if we just see observed language or measured language or quantum mechanical language. So I just write it here. If it's observable language, it's quantum mechanical language. So this is measurement. So if it is U, so it's true. If it's U, so you have a measurement on this thing. If its measurement is true, this is true, it will be also be true. If this is true, this is false, it will be false. Now, if its measurement is false, it is true, it will be meaningless. If it is false, this is false, it will be again meaningless. So only true, if measurement is true and the quantity you are going to measure, they are both having some value, so you can have this thing. If one of them is this, so in that sense you can say. And the fundamental thing is that how we can eliminate anomalies. So in our earlier interpretations, in the beginning part of the course, how we did away with causal anomalies. We had either exhaustive interpretations or the restrictive interpretations. In restrictive interpretations, we took the corpuscular path and we just did away with things. In the same way, but it did not account the whole of the thing. The description cannot be said complete. While in the exhaustive description, we could account for things. So you can say in that context, what this once we say this Bohr-Heisenberg, that measurement is only assigned after you things. You don't take measurement. You don't take the value not prior but after measurement. Once you measure things, we assign that thing. So it becomes a sort of very narrow thing statement, in the sense that it only uses verifiable statements. Among the so in principle you can have all statements, but you are forced to choose a certain statement about this thing. And it uses a weaker definition concerning unobserved entities rather than interpretations. So this is a way of just doing away with those anomalies. So you can say that these verifiable statements can be taken in as those having restricted meanings, as far as what do you mean by them. So in that sense, you can one was complementarity principle, that measurement of one can happen at the expense of other. The accuracy of one depends upon the other. If one is measured more accurately, the other will be measured, conjugate variable measured more less accurately. So if it's just stated in a theorem which says, so if two statements are meaningful, if one is meaningful, other is meaningless. Maybe to my understanding, it should have been, if one is more meaningful, the other becomes less meaningless. The more we make one precise, the other becomes imprecise in that sense. Now you can have this is this thing, and you can now, these are definition 4, 5, and the last definition which I am going to write is like this. Definition 6, which says that a quantum mechanical statement, statement U is meaningful if it's possible to make measurement. If it is possible to make measurement, it's possible to make. So again, come to what do you mean by meaningful. So the thing is that so we can say meaningful and meaningless is also seen what can be connected, what cannot be connected. For example, in your very definitions, there is an exclusivity on the problem that we consider two simultaneous observables if they are non-commutative in that sense. So they cannot be measured in that exact sense. So you exclude a lot of possible statements which are not, which can be, you can classify them things which can be connected and which cannot be connected in that sense. So in quantum mechanics, statements like P and Q are meaningless. What I should say, P and Q, or P or Q. We have statements P and Q. Is it not possible to make statements like P and Q is meaningless? Similarly, other combinations are considered meaningless like P or Q. That's what I'm saying. So again, it's the problem of what I should say, connecting what is observable, what is symbolically assigned to it, and what are the restrictions imposed by quantum mechanical language vis-a-vis what we have studied today. So we'll continue it.